chapter 21. So what I wanted to do was, I'm going to erase this. So, does that answer your question? I mean, your issues, or yeah?
Yeah.
So, we'll just go along. If I give you 80%, then, you'll be more likely to do the homework and enjoy it, as opposed to having an anxiety attack over this same problem that, doesn't give me the right answer when you know it's correct, or you don't find any mistakes in it, right? So, yes?
So are you going to grant us credit for that question, 2D?
As they fix it, then I like to fix it, and I can grant you credit for it, yeah.
Okay,
Yeah,
thank you.
sure. So that at the end, I don't want you to get less than 80% because there were so many of them that, then, yeah. So,
Thank you.
yeah. So anyway, the question was the ring problem. So, I'll just mute the video, not turn it off. So if, let me do the ring again, because it's relatively simple, right? So we look at a point on the axis of the ring. The radius of the ring is A. I mean, there is an expression that we derived already. But what the heck, let me do it again to show you that it's no big deal, actually. So suppose the total charge is Q. So the total charge on the ring is Q, and it's uniformly distributed, right? So the way that we did it is we said, okay, let me think of all of this charge as being distributed over a length, ds. I don't know if I called it ds, but maybe I did, right? So the s is the length over which this charge dq is distributed. All right? But if I think of that as a point charge, it generates an electric field here pointing away from the point charge, right? Because I made the point charge positive. So therefore dq would be positive, and it will produce an electric field that points away from it. Now from symmetry, I can tell that the component of this electric field along the x-axis is what's going to survive. Right? So that component would be this. And that's the E, but it's the x component of that, which is just the E sub x. And the x component of the E is just the magnitude of the vector times the cosine of the angle theta that's given in the diagram, right? And dq is the electric field generated by, dE is the magnitude of the electric field generated by the charge over here, dq. I can think of this as a point charge, kq over r squared. So it would be k times q, but that one is dq, divided by r squared, where r is the distance from the q to the field point. Yes? So this becomes that. So that's the x component at this distance x from the center of the ring, produced by this little bit of charge dq over this length ds. What I want is the electric field there to all the charge. So I need to add all the other contributions from the next dq, from the next dq, from the next dq, from the next dq, and all of them are going to have an x component given by that. So to find the total electric field, I just do the sum. So I, do the sum. So the integral of this is going to be e sub x. Now here, k is a constant, so I'm going to take it outside the integrand. R, for every dq that I choose, the distance r to the field point on the axis, on the x-axis, on the axis of the ring, is the same distance r. I don't care. This is like a cone, right? So r squared is a constant. The angle theta, this angle theta is the same as this angle theta, and that's going to be the same for every dq that I choose. So that's also a constant. And then I'm left with the sum of all the dq's. And if I add this charge dq to the next little bit of charge dq, to the next little bit of charge dq, to the next one, all the way around, I'm just going to get this capital Q. Right? So this integral here is just the total charge Q. I mean, people, they say, oh, from 0 to capital Q, but I don't like to do that. To me, I rather think of the sum of all the dq's is just the total charge in the thing, right? So that's what I prefer. Okay. All right. So that the electric field is K, Q, cosine of theta over R squared, right? Now, we were not given R, we were not given theta, so we need to express our answer in terms of the given quantities. We were given the radius, we were given the distance x, and we were given Q. So my answer should not have this R because that's something that I put in, and it shouldn't have theta because that's something that I put in. So, well, the cosine of theta is what? X over R. So this combination, cosine theta divided by R squared, is X over R, well, divided by R squared. So this will be X over R cubed. And that's going to be X over, that's R, but then I have to cube R. And that's going to be X squared plus A squared. Yes? So, you know, this times that, I mean, this goes in there, right? So that, and I can get a little fancy. I can say the electric field points in the positive x direction, just give it a vector notation, and the magnitude is going to be K, Q, X over and that's the answer. Yes? Or did I make a mistake? Let me look at my answer. Okay, so here's another way to do the problem of the disk. I want to use that answer. So I'm just going to copy down this answer over here. So I know that if I have a disk, a ring of radius A, and I want to go at this is X on the axis, right? And the total charge on this is Q. That's going to produce or generate an electric field on the axis. This way. Q is the charge on this ring here, right? K, Q, X over. Is that right? Did I copy that thing down? Okay. This thing probably is going to shut down again. That's what it's doing now. Yeah, I guess it's like to save the bulb's, energy. Yeah, so that's this problem. The question is, how can I use this to solve the problem of the disk? Any questions on that so far? I mean, it's like the second, third time that I've done that problem, but. So can I erase all of this? Sure. So this is the product of the ring. Now the ring, the disk is a little bit more complicated. But I can think of the disk as being built up by rings. A whole bunch of rings will make the disk, right? So that's what I'm going to do. So. So then, what about the disk? So the disk is this. The radius of it is, I'm gonna give it A. So, but this is a disk, right? And this is X. And the total charge on this is plus Q. Right? Notice, this plus Q is the total charge on the surface of the disk. It is not the charge on the ring. Right? Here, A, can you see this? It's sort of at an angle. A is the radius of this ring, so this is the ring, right? Q is the total charge on the ring, right? X is the distance from the center of the ring to the point. Now Q here is the total charge on the disk uniformly distributed. A is the radius of the disk, right? So what I'm going to do is I am going to find the electric field produced by all that charge on the disk, right, at this point. So I'm going to consider a ring like this. And I'm going to give it a thickness, a radius r, and a thickness dr. And I don't remember which r I used in my notes when I saw this one. Did I call this? I just don't remember. Can I call this distance r and the thickness dr? Or did I use the other r like this?
You used the squiggly R.
This one?
The
No, that was the
cursive one.
distance to that.
So it was this one?
Oh.
Did I write my r like that?
I think it was just regular.
I think it triggered.
It was right.
It doesn't. It won't matter in the end, but just wanted to be consistent so that. All right, and then this is the Q. Right? In that ring of radius r and thickness dr. Now, using this result on this side, what is the electric field produced at this point, which is at a distance x from the center of the ring this way? What will be this electric field produced by this charge dq in this ring? So then this electric field here would be, I already did the problem of solving for the electric field there produced by this ring. So it would be what? It would be Coulomb's constant times Q, where Q is the charge of the ring. So it would be Coulomb's constant times the charge of this ring, which I call dq, times x, which is the distance from the center of the ring to the field point. That's the same x over here. And then in the denominator, I have x squared, where x is the distance from the center of the ring to the field point, plus a squared. Now, what was this a? This a was the radius of the ring, right? So here, the radius of this ring is not a, but it's this r. So then I have to do this. Agree? Yes.
Could you say again y is plus but not minus?
By what?
Could you please explain why is the plus but not minus?
Why this is plus? Or why this is plus?
That one.
This one? That's what we got over here. It's x squared plus, that was the result of the problem that I just did. Because, yeah, if you look at what I did for the ring, right, you had something like this, and this was a, this was x, and then this r was, it's a different r. That would be square root of x squared plus a squared. So this plus is this plus. Yeah, so it was a Pythagoras theorem type of thing. But then we wanted r cubed because we had a cosine of theta over r squared. But the cosine of theta was x over r, and then you still had the r squared. So this is x over r cubed, but r itself, r is this. But then we gotta cube that. So that's just cubing it. questions if you have them. I'm here for you guys. If I'm doing it on the board, it's because I know how to do it. So I want you to learn it, right? So if you have questions, that looks weird, by all means, ask me. Okay? So, and if I don't know, then I'll ask you, help me out. But are we okay with this expression here? So now, this is the electric field. Notice it's already pointing along the x-axis, right? Produced by the charge in the ring. So what I want is the electric field there due to the next ring, and the next ring, and the next ring, and the next ring, until I fill up this disk with rings. So all I need to do is integrate this, to do that sum. And the integral of the E is E, and I can get fancy, I can do this, right? Okay, it's along the x-axis, right, so on. Now, K is a constant, correct? Is X a constant? If I choose different rings, is the distance from that point to the center different or the same? The same, right? So X is a constant. I have a dq. And then, is this a constant? As I choose different rings. Well, as I choose different rings, the X in here is a constant, because from here to the center is the same, but then the R, the radii of the rings are going to be different. So then this R is a variable. So I got to keep that inside. In fact, I like to put the variable first and then the constant next. Like that. Now, what did we say? We're integrating with respect to Q. But here, X is a constant, while R is not a constant. So I gotta find out a relationship between R and the Q. So what is the Q? Remember what we said about this, the Q? Remember the physicist expression for dq? It would be the charge per unit area, which is Q over pi a squared. That's the total charge, right? It's normally called sigma. Charge per unit area multiplied by this area, which I called the A. And the area of the A, remember what it is? If you cut it and you stretch it, what would it be? If I cut it like this and I stretch it. The thickness is the R, but what is the length? 2 pi r, the circumference. So therefore this would be Q over pi a squared times 2 pi r the R. So now I take this and I plug it in here for dq. And notice that this pi cancels this pi, so therefore this becomes. Now, what can I pull outside? I got a 2, I got a capital Q, I got an a squared in the denominator, and then I have an RDR, right? And then I have this other one, like that. And now I just have a variable R, and X is a constant, and the integral is with respect to R, so therefore my limits of integrations must be values of R. So I have to integrate over rings of radii R. So if I consider the first ring, what will be the radius of that? 0. And then the next ring, and the next ring, and the next ring, until I get to the last ring, and what will be the radius of the last ring? Just A, so I integrate from 0 to A. And then you can say, oh, how do I do this integral here? Now that's a calculus 2 problem, or maybe calculus 1, actually, at the end of calculus, well, whatever, whenever you learn how to do this type of integral. So if you say I, I'm going to define that as r dr, and this is r squared plus x squared to the 3/2 from r equals 0 to r equals a, then, okay, so I'll let u be r squared plus x squared. So du dr is going to be 2r. I see that I have r dr over there, so I'm going to, du over 2 is r dr, so I can take this and put it upstairs. So this is the integral of 1/2 of du, and then the thing inside is what I defined as u to the 3/2. So this would be 1/2 of u to the minus 3/2 du. So this is 1/2 of, and this is u to the minus 1/2 over minus 1/2. So this is minus 1 over u. Yes or no? But then u is this. So the integral equals, this 1/2 cancels that 1/2, so it'd be 1 over the square root of r squared plus r squared, right? Plus x squared. And then I have to evaluate this from r equals 0 to r equals a. And just so I don't have to deal with that minus sign, I can get rid of the minus sign and just flip the limits of integration. So this would be 1 over the square root of x squared plus r squared from a 0. Now I get rid of this minus sign by flipping the limits. So this is what? 1 over, if I put, and this is from r equals, if I put this one first, that'll be 0, so that'll be 1 over x, correct? Minus 1 over the square root of, right? That's the integral. And then I have to multiply that by this. Right? To get the electric field. So the electric field will be so you have 2kqx over a squared times the integral, which is 1 over x, minus 1 over the square root of a squared plus a squared. And now I can take this x and I can multiply it through. And I'll get I hat 2kq over a squared, and then I'm going to get 1 minus x over the square root. And I don't know if I express the answer in terms of capital Q or sigma, the charge sprinted area. Well, that's what it would be. If I wanted to express it in terms of this, notice that, I don't know, is that the answer that I got, or did we could express K in terms of what's called the electrical permittivity of free space, and then Q is sigma times pi a squared. So I can take these two guys and I can plug them, in here and there, and then get an answer in terms of epsilon naught and in terms of sigma. How about we do that? Can I erase this here or no? Can I erase this? Or maybe can I erase this up here?
Just leave them in black, please.
Huh?
Just leave the black part, please.
Okay, so I'll just erase this at the top. In fact, I'll erase this too. So the expression that I have for the electric field is there's a 2, instead of K, you can put 1 over 4 pi epsilon naught. And then instead of Q, you can put sigma pi a squared. And then we have an a squared in the denominator. And then 1 minus x over. All I'm doing is algebra. And this pi cancels that pi. A squared cancels that. The 2 and the 4 gives me that. So we get I hat sigma upstairs, 2 epsilon naught downstairs. So this is probably how I wrote it last week. But this is just as good an answer. This one here. Just as good an answer. And I hope if you check with what I did last week in your notes, I hope I got the same result. I mean, I don't think I did, but, you know, check. Check things. Yes, cool. So I've done that problem in 2 ways. Right? I actually think this way is easier because we exploit the result of that we get for the ring instead of starting like totally again. Should I leave this up? No.
Sure, yeah. Put some fresh air in.
Oh, by the way, YouTube since probably most of you haven't taken classes at OCC yet, other than online. You see this thing over here is called the lock block. So if you need to go to the restroom, just go, right? And then you can just push this out. So you can put it in, or out, put it out, and then it doesn't lock. And then you can go out, and then nobody has to open the door for you to get back in. Now, you're sitting next to it now, right? So if someone else is sitting here next time, I leave the door locked from the outside. It's locked. Now I leave it like that so you can go in and out during class. But if you hear somebody shooting or something outside, get up. You're the one up. You'll be able to get here closer to eye time from up there. Just and then it's well from outside, from wherever is outside. So that's the purpose of this. That's the main purpose of it. Right? But another use is so you can go out and not have to knock on the door to get back in. But that's OCC, the whole campus has those things, and that's why they were put in there. Actually before the pandemic. God willing, that'll never happen. But that's what they're for. So just quick, you guys, whoever is there, then all right, any questions? Not about that, but about this.
Where did we get the formula for the total charge Q?
So sigma is the charge per unit area. So sigma is the charge per unit area. So if I want to know the charge, it would be sigma times the area. So if this is the total charge Q, then this has to be the total area of the disk, which is pi times the radius squared. Yeah. Sometimes you'll see lambda is the charge per unit length. So the charge equals lambda times the length. Now, suppose you have something like, can I erase? Oh, I'll erase this here. Suppose you have something like this. I think there was a problem where we said that the total charge on this was Q, but I think I made the total length of this 2L. I mean, it could be L or it could be 2L or whatever, right? So therefore, the total, if I once, if the charge here is all of that charge along that line, it will be the charge per unit length multiplied by that length, which is 2L. So lambda is usually used, it's a Greek letter, I think it's their L, lambda L. So it's a Greek letter that represents the charge per unit of length. So you have this thing, if you consider 1 meter of length of that wire, for example, the charge is lambda. And then the next meter, the charge is lambda. The next meter, the charge is lambda. But if you have, for example, charge distributed over this wall, so the total charge of the wall will be capital Q. But if they ask you what is sigma, well, it would be all of that charge divided by all of this area. And that will be the number of coulombs per meter squared. So sigma is equivalent to, you can think of, suppose this is 1 meter, and this is 1 meter, so it will be the charge, sigma is the charge in a surface of area 1 meter squared. And sometimes you have charge distributed throughout a volume, and the symbol that they use for that is rho, the Greek letter rho. So it's the charge per unit volume. It means if you suppose this room, there's a solid that fills this room, and the total charge in this room is capital Q. So what is the charge in 1 cubic meter of volume? It will be rho. Is the charge, total charge divided by the volume, right? So then the total charge will be rho times the total volume. Yeah. Other questions?
Is it more just, is that lowercase rho? Because I feel like I'm used to seeing rho as like backwards 6, right?
No, that's like a delta.
Oh, am I getting yeah, that's
That's
delta?
like partial derivatives. That's like a D,
Oh, okay.
I think.
Is that?
I'm not Greek,
Okay.
but I think that's the case. Yeah. I mean, I kind of could pass for Greek because when I was living in New York City, there are a lot of Greek. Well, New York City has a lot of everything, and over there I get, you're Italian, you're Greek. Here in Orange County, they think I'm Persian, but I'm not Persian. So, but yeah, rho and yeah. This is delta, which is, I think that's the capital delta. This is the lowercase.
Oh, okay.
Yeah. Anyway, I don't know what the capital rho is. I think it's an R, but I don't know what that. I don't know. I don't want to guess. Okay. So, can I erase this?
Mhm.
Any other questions? What you should do is, look at how I did this in your notes, put it away, and then do it yourself from beginning to end. Let's see how far you can get. And when you get stuck, then you look at what you did, and then, in your notes, and then you continue. But don't keep looking, just keep doing it, right? Yeah, do it a few times. If you can't fall asleep at night,
Oh God.
if you can't fall asleep at night, then you can.
This will put you to sleep.
Then you can just get up and do this stuff. And if you get it done, then when you go back to bed, you say your prayers and then you'll fall asleep.
Professor,
Yes.
is this what you do every night?
Actually, last night I was excited because I was going to be here today with you guys.
Oh, okay.
I woke up, I set my alarm clock to 7 o'clock in the morning, but at 6 I was like this. Eyes wide open. Anyway, I enjoy teaching in person much more than on Zoom. But that's just my thing. So I think this is a lot easier. I think this is a lot better for the students because you can see on the board the beginning and how the solution to the problem progresses. Whereas you know how you guys say, oh, can you go back one page, and because I cannot write small anymore like I used to at some point, and to try to fit it all in a page in my iPad. So. Okay, good. Okay. The next chapter, I gotta turn this baby on again, is Gauss's law. And Gauss's law is a trick where we exploit symmetries in the problem, but it's a trick for solving for electric fields. It's a very powerful trick, but it only works sometimes. It doesn't always work. Or, it works all the time, but it is practical to use only sometimes. Okay? And so that's what I would like to discuss next. It's called Gauss's law. And it looks a little intimidating, but there's really not much to it. I'm going to try to do a lot of geometries, and then, by the end you'll see it. We need to know, though, areas and volumes of spheres and cylinders. But it's only spheres and cylinders, so it's not so bad. Okay? So we have Gauss's law, chapter 22. Let me see if I can put on some lights. Electric flux, we don't even need to talk about that. We could, but this is Gauss's law. So Gauss's law is you have an integral with a circle in the integral sign, which means something. And then there's E dotted with an area vector. And then on the right hand side is epsilon naught. The K is 1 over 4 pi epsilon naught. Remember, Coulomb's constant is 1 over 4 pi epsilon naught. So it's this guy that appears in the denominator there. And then we have Q here enclosed. So first of all, Gauss's law is used only in certain problems when you have enough symmetry. And what I did is I created a table here to show you for which problems you can use it. So we can only use Gauss's law if you're given a point charge. Actually, we already know what the result is for the electric field generated by a point charge. We know that it is Q over R squared. If the charge is positive, it's away from the point charge. If the charge is negative, it is towards the point charge. But we're going to use Gauss's law to derive that result for the electric field generated by a point charge at some distance or away from it. So if you have a point charge, you can use Gauss's law. If you have a sphere with, if you have a sphere, then we can use Gauss's law. Okay? Usually we use it very quickly if the charge in the sphere can have only a radial dependence, a distance on R from the center. but or uniformly distributed, either uniformly distributed or maybe the charge per unit volume has a radial dependence. So with spheres, we can use Gauss's law. If we have a very, very, very long wire, here it says infinitely long wire, but there's no such thing as an infinitely long wire. But if we have a cable from one post on the street to another one, and you see the cable, right? And if you go somewhere in the middle of that long cable, and you go 1 inch, a centimeter above the cable, the result that you get for the electric field can be obtained using Gauss's law. Right? So a very, very long wire with charge uniformly distributed throughout the wire, then we can use Gauss's law. Or a very, very long cylinder. It could be a tube, a solid tube. It could be a hollow tube. That's very, very, very long. We can use Gauss's law. And the other one is an infinitely large sheet. So like a wall, like all of that wall, for example, suppose there's charge distributed uniformly throughout the wall, and if I go somewhere near the middle so that the edges are far away, and I go 2 millimeters away from the wall, then the expression that we get using Gauss's law for the electric field is a very, very good approximation to the truth. So these are the only problems that we can actually solve using Gauss's law. So point charge, a very, very long wire, actually spheres too, and then a plane of charge. I speak with an accent, so I should be careful when I say sheet. I gotta stop and say. So a plane of charge uniformly distributed, right? That's very large. Then if you're very, very close, we can solve these problems without having to do the dq and r square and then do the integral and variables and so on. We can avoid that for these problems. Notice, we did a problem in class, I think it was the week before last, where we had a finite wire, of length 2L, and then we went like some distance above the midpoint. So that wasn't an infinitely long wire, so we couldn't use Gauss's law. We had to do the integral. Today we did the ring. Notice there's no ring over here. It's either a point charge, a sphere, very long wires or very long cylinders or very large sheets. So the ring problem, the disk, we gotta do the way we did it, with the integral, and you gotta set it up. So those problems we don't solve using Gauss's law. The ring, the disk, a wire of finite length, and maybe you want to know the electric field here or above. You cannot use Gauss's law. It's gotta be infinitely long, or very, very, very long, or a very long cylinder. Spheres. The spheres could be hollow, and large sheets, or combinations of parallel sheets. Then we can use Gauss's law.
Excuse me, Professor. Why do you differentiate between a long wire and a long sphere? Cylinder. Sorry. Is there a difference? Wouldn't a long cylinder be the same thing as a long wire? I messed up my words. Wouldn't a long wire be the same thing as a long cylinder?
Yes, except that if you have a thin wire, for example, then you only talk about what the electric field is outside of it. Okay. But you could also have a tube, like a solid tube, with charge distributed, throughout. Maybe it's an insulating, a dielectric, not a conducting material. And so you can talk about what is the electric field inside and what is the electric field outside. So if we're going to talk about the inside, then we got to give the thing a radius. And then, okay, it's got some diameter and some radius.
Okay, so wire wouldn't have radius? Is that the right way?
Wire usually, if it's thin, then you could just say, well, the radius is A, and then we can find it inside like you would for a cylinder. So for a cylinder, it's like I'm thinking inside and outside of it.
Okay.
A thin wire is like I don't care about the inside, only the outside.
Okay.
But they're really the same, basically, yeah.
Are we ever going to have problems where the wires, cylinders, or sheets are going to be infinite in terms of they're going to be constantly expanding, or the radius will be changing, the size will be changing? Or just be assuming that.
Yeah, so you're going to have a given geometry, so the radius is A, but it's very, very long. And you wouldn't be given, for example, for the infinitely long wire, cylinder, or sheets, you would not be given capital Q, the total charge. Because if it's uniformly distributed, what would be the total charge if the thing is infinitely long? if I have 2 coulombs per meter, 2 coulombs per meter, 2 coulombs per meter, 2 coulombs per meter, and so on, when this thing is infinitely long, what will be the total charge?
Infinite.
Infinite. So you're not specified, but you're not specified what the total charge is. But for those problems, lambda, the charge per unit length, that's specified.
Okay.
And the same thing with the wall, for example. Then, well, if the sheet is infinitely large and the charge distribution per unit area is the same, sigma, then the total charge is going to be infinity. So you're not given that. But you can talk about the charge per unit area. So sigma becomes important. And for the spheres, for example, or cylinders, well, in the case of the spheres, you can talk about the total charge Q because you're going to be given a radius, so the thing is not infinitely large. But you can still talk about a charge per unit volume. And in this case, if you have a cylinder, we can talk about the charge per unit volume also, rho. Even though, but if this is infinitely large, then the total charge will be infinity, but you can still talk about the charge per unit volume, rho.
Okay.
And you'll see, I'm going to do, and not only do I want to do just cylinders, but I want to do a cylinder that's a conducting material, like made of copper, for example, or a cylinder made of wood, or something that's non-conducting, rubber, or something that's non-conducting. So there's going to be a difference in the calculation of the electric field inside and outside the thing. So I want to consider spheres that are conducting and spheres that are non-conducting. Okay, so I mean, I'm going to do a lot of examples. So I'm going to start with a point charge, and then I'm going to do a sphere, and then I want to do spheres that are conducting and spheres that are non-conducting, and I want to do spheres that are hollow with a hole cut out inside, conducting, non-conducting, and then I'm going to do a wire, and then I'm going to give it a radius, and then I'm going to call it a wire, a cylinder, and then conducting, non-conducting. And then we'll finish with the sheet. And then we'll do multiple sheets. Then
How about the disk one? It's not applicable, right?
the what?
The disk problem? You said the ring is not applicable with Gauss law. How about the disk problem? Will it be the sheet one or?
So the disk, so remember that last week, I think, the last time that we met, I took the expression that we derived today for the electric field generated by the disk, and then I took a limit. What happens if you're very, very, very close to the disk? What will be the electric field if you're very, very, very close to the disk? Like x is very, very small compared to the radius a. And we got an expression. And that expression, because you're so close to the disk, we can say, okay, let's see what we would get if we use Gauss's law. And we're going to get the same answer. But only in that case, yeah. If the disk is like this and you want to know the electric field somewhere over here, then this charge is not. This is not an infinitely large sheet. It's not an infinitely large area, right? So then no, you gotta do the integral. Okay, I guess I'll. I don't want to fight with this thing here. Could you give me some lights again, please, in the front? Thank you. Saves me a trip. Thank you. So, let's talk about what the different things mean in Gauss's law. So, the circle that you see here means that you have to consider a closed surface. And that surface, see, in Gauss's law, you imagine a closed surface, something that you imagine. So you have to imagine a surface, but the surface has to be closed. Okay? So it's a closed, and that surface that you imagine is called a Gaussian surface. So it's a closed Gaussian surface. The E that you see here is the electric field at the surface that you imagine. And what do we call that surface that you imagine? a Gaussian surface. Right? So this is the electric field. So you imagine a surface, and that E in that integrand is the electric field on that surface that you imagine at the Gaussian surface. This quantity is the area vector. Ooh, an area vector. What is that? So it's an area vector of the Gaussian surface that is perpendicular to that surface that you imagine and going outwards. So it's an area vector of the surface that you imagine called the Gaussian surface. And perpendicular to the Gaussian surface and I should say another and, I'm sorry, and going or pointing outward. So, for example, so in this case, I also did the following. So notice, I said that you can use Gauss's law for a point charge, for a sphere, for an infinite long wire, infinite long cylinder, infinite large sheet. Now, for those geometries, you imagine a surface. What are the surfaces that you imagine? That's what I wrote on the right-hand side, in this column. So, for a point charge, you imagine a sphere. That's a closed surface, right? For the spheres, you imagine a sphere. That's also a closed surface. For these three other guys here, you imagine a cylinder. And you have to consider, and it's a closed surface, so you gotta consider the, like if this is the cylinder that you imagine, you gotta consider this area, and you gotta consider this area and this area, so it's closed. So you can talk about the inside and the outside of the surface that I imagine. So we only imagine either spheres or cylinders. And the A stands for the area vector. So for example, if you imagine a sphere, well, what is the direction of that's perpendicular to the sphere? That's that one. The A is perpendicular to the sphere. What about if you imagine this cylinder? Well, at that point, the A is perpendicular to that. If you think of the A of E here, it will be down. On this face, the A will be to the left. On this face of the cylinder, the A will be to the right. What if you imagine this cylinder? Well, same thing, right? So the thing in purple is the Gaussian surface that you imagine. And the other color here, that's what you're given. The infinite large sheet, an infinite long wire, a point charge. Right? So just remember that this is an area vector that is perpendicular to the surface and pointing outwards. Because the surface is closed, so pointing outwards, not pointing inwards, but pointing outwards. And the area vector is just a vector whose magnitude is the area of the thing, of the surface. If I ask you, what is the area vector of this surface over here? Well, the magnitude will be length times width, pointing up. Although, because this is not closed, I could also say pointing down. But if it's closed, then I see an outwards direction, and then it'll be the outwards direction. Notice, this is not just any multiply by, this is a dot product. So what we need to do is consider the electric field at various points in the Gaussian surface, draw the area vector at those points on the Gaussian surface, and consider the dot product of the electric field vector with the area vector. And if you remember, when you multiply two vectors using the dot product, what do you get? Do you get a scalar or a vector? A scalar. Notice that the right-hand side of this equation is a scalar. Charge is a scalar, and epsilon naught is just a number. So this is a scalar because the left-hand side, only a scalar can be equal to a scalar, right? So the thing on the left, this integral is just going to be a scalar quantity. Right? So that's why these two vectors are related by the dot product. This Q enclosed represents the total charge inside or enclosed by the Gaussian surface. So you imagine a surface, and it's the total charge inside of the surface that you imagine. So the E and C, I write it like that. It means the total charge enclosed by the Gaussian surface. So this is, and epsilon naught is just a constant. This is the total charge enclosed, which means inside So, well, with Gauss's law, you imagine a surface. Does the surface exist? No, you just imagine it. I think I wrote a comment to that effect over here. So I said, here, Gauss's law is used to calculate the electric field generated at some point by some charge distribution. On a sphere, on an infinitely large cylinder, on an infinitely long wire, on an infinitely large sheet, right? That has enough symmetry, that's infinitely large and so on. Right? Here you imagine a closed three-dimensional surface. You're only going to imagine a sphere or a cylinder, and then consider this integral. And I wrote this, my very first comment is this: the surface that you imagine is not there. You're seeing things that are not there. As a trick to solve a problem. But they don't exist. They're just something you imagine. The integral, the circle in the integral sign means the surface that you imagine has to be a closed surface. Well, spheres and those cylinders that I said are closed surfaces. E in this expression is the electric field at the Gaussian surface. The A is an area vector with magnitude equal to the area of the Gaussian surface, and the direction is perpendicular to the Gaussian surface. Well, is it perpendicular going outwards or inward? Outward. And what's Q enclosed? Well, is the total charge inside the Gaussian surface that you imagine. And Gauss's law is only practical in some cases with enough symmetry. This integral over here on the left-hand side is called the electric flux, but we don't need to give it a name. They call it the electric flux, but I don't care what they call it. And then we do problems. Oh, this is going to become important. So, what if you have a conductor in electrostatic equilibrium? That would be a conductor that has been charged, and then the charges are not allowed to move. It's like, suppose I have a sphere, and I charge it, and then I leave the sphere alone. And so the charge is there. It'll go here, there, and stay put. Right? So, or an infinitely large sheet, right? So it's charged, and the charge is plastered on it, and it's not going anywhere. So, if that's the case, the electric field inside the body of the conductor is going to be zero. It's really cute. If you imagine a sphere, a solid sphere, metal sphere, and I charge it, it's like the charges say, oh, wow, that guy just transferred us to this sphere, and it's metallic. Well, let's move around and let's do something so that the electric field inside the sphere is zero. And you know what they do? They go to the surface of the sphere. And it just got erased.
That's going to get in one too.
So, if you have a conducting material in electrostatic equilibrium where you charge it and then the charges are not moving anymore, then the electric field inside the body of the conductor is going to be zero, and any net charge that the conductor has will go to the surface or to the surfaces. Because what happens if the conducting sphere that we're interested in is hollow? It's got an inner surface and an outer surface. So some of the charge may go to the inner surface and the rest of the charge will go to the outer surface. And how much goes to the inner surface? How much goes to the outer surface? I'm going to teach you how to figure that out, and you're going to know the answer in less than 2 seconds. Isn't that cool? It's like I'm going to say, how much is here, there, and in less than 2 seconds you'll know the answer. It's just going to take you longer to say it. Okay, that will be 3 seconds to say it, but it's going to take you longer to say it than to know what the answer is. So we're building to that level where you can just, of course, it's going to be this charge. Remembering that if the conductor is in electrostatic equilibrium, where you give it a charge and then the charge goes to the surface or surfaces and stays there, then that's when it is in electrostatic equilibrium. And then, now, if you take a wire, are you connected to the terminals of a battery and the charge is going around, that wire is not in electrostatic equilibrium. It's like you charge it and you leave it alone. Keep the charge, keep it there. Okay, so I say that. Okay, that's it. We don't need this anymore. So I want to apply this. How about we begin with the point charge? Right. How much time do we have?
Till 5:30, I think.
5 minutes.
We have
45.
45 minutes? Okay, thank you. Cool. So we're going to do, how about we start with the first one? The first one that I had in that table was the point charge. And we know what the answer is, right? So let's, apply Gauss's law. So, number one. A point charge plus Q. So here's the point charge plus Q. And I want to know what the electric field is here. What's the electric field right there? We know the answer, right? What's the answer?
0.
K cubed R squared pointing which way? Away from it, right? So what we do is, well, we were just given a point charge. And what is the surface that we imagine? Then I go to my table here, and I say, we were given a point charge. So I am going to imagine a sphere. Is there a sphere in this problem? No. We're going to think that there is, but there isn't. There's no sphere. So, well, the sphere that I imagine is with the point charge at the center of that sphere. And this sphere that we imagine is the Gaussian surface. So that's my Gaussian surface. And I write Gauss's law. And I'm going to do this in detail, but then you'll see how we're going to take a shortcut. So Gauss's law is by the way, a little aside. If I want to know the dot product of 2 vectors, right? Because I have a dot product of 2 vectors. How do you calculate the dot product of 2 vectors? Do you remember?
Isn't it AB cosine of theta?
Exactly. It's the magnitude of A times the magnitude of B times the cosine of the angle, the smallest angle between the 2 vectors. Right? That's how you calculate the dot product of 2 vectors. Okay, so remember, the circle means in the integral sign, it means that the surface that I imagine is closed. Well, I did. This is a sphere. It's closed. This is the electric field on the surface. So let me choose different points on the surface, right? And ask, what is the direction of the electric field here? What would you say? electric field produced by the point charge, right? Away from it, right? What about over here? Away from it, right? What about over here? Away from it, right? Away from the charge. Okay, so I picked 3 different points on the surface, right? The Gaussian surface that I'm imagining. Next, how about the area vector? Remember, I gotta take the dot product of those electric fields with the area vectors at those locations. So now, what do we know about the area vector? It's perpendicular to the surface going. So perpendicular to this surface and going outwards is which way? It's this way, right? What about over here? Perpendicular to the surface and going outwards, right? And over here, well, at that point, it's going to be perpendicular to the surface and going outwards, right? What do you notice? I gotta take the dot product between the electric field and the area vector. What do you notice about the angle between the electric field at the surface, the Gaussian surface, and the angle of the area vector?
It's 0, so it'll just be
It's
magnitude
0
times
throughout,
magnitude.
right? So here it's 0, here it's 0, and here it's 0. So when I write this here, it would be the integral of E. The magnitude of E is E without the arrow times the A. That's the magnitude of that without the arrow, because it's the magnitude. I mean, I could do this, but I think it makes it too confusing. I'll just write down the magnitude of the vector without the arrow above it. So instead of writing it like that, fancy, which may be confusing, I'll just call it E without the arrow. That's just the magnitude, the A. And then I have the cosine of 0 degrees all over the place. Which, by the way, is?
1.
1, correct. And all of that is equal to, I have the constant downstairs. And what does Q enclosed represent? In Gauss's law, what does it mean? Is the total charge inside the Gaussian surface that you imagine. Now look at the Gaussian surface that we're imagining. What's the total charge inside of it?
Q.
Just a point charge, little q. Does it matter where it is inside? No. It could be in the corner over there. I don't care. It's inside. That's all it is. Now, why would I pick a sphere when calculating the point charge, the electric field generated by point charge? Well, I know that the electric field drops with distance. And if I consider a sphere with a point charge at the center, all of these distances are the same. Yes? If the point charge is at the center, if I go to the surface of that sphere, then everywhere on that surface, the magnitude of the electric field should be the same, because they're all at the same distance away from the point charge. So therefore, this electric field that I have over here, throughout the entire surface that I'm imagining, is constant, because I'm not the same distance away from the point charge. So therefore, I can take this guy outside, which is what I'm solving for. The cosine of 0 is 1, and then I have this. Yes or no? That's the reason why, for a point charge, imagining a sphere works. But this is the sum of all the area elements around the sphere, the Gaussian surface. So what is the area of the Gaussian surface? What's the area of the sphere radius r?
Infinite?
Surface area of a sphere.
Oh.
That's a circle. Pi r squared is a circle, but it's a sphere.
Oh, sphere, oh.
What's that?
4
4 pi r squared, correct.
So,
So close. So far.
Yes? Right? Because this integral is the sum of all the area elements. That's A, which for the surface, right? Which is 4 pi r squared. Now let me solve for the electric field. If I solve for the electric field, I'm going to have, the magnitude is going to be, I know the electric field is away from the positive charge, then I'm going to have 1 over 4 pi epsilon naught, right? Q of r squared. But what is this?
Okay.
Okay. Which is the result that we knew from chapter 21. So we can use Gauss's law to derive, if you like, that expression. So, does this sphere exist? No, it's not there. You want me to find out the electric field over here? I will imagine a sphere passing through that point. Put the charge at the center. And then, boom, 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 and an answer. Questions? Are we ready for the next? Okay. How about we consider a sphere? Let's do a conductor. What are we supposed to remember about the conductor? If it is in an electrostatic equilibrium, then what?
Zero.
If it has a net charge, it's going to go to the surface or surfaces. And what else?
The interior is zero.
Inside the body of the conductor, like if you could eat the conductor inside there, what you would eat? The electric field is zero.
The charge inside is zero, right?
Well, the charge goes to the surface or surfaces, making the electric field inside the conductor equal to zero. Yeah? Okay. So let's do a sphere. Let's do the conducting sphere, and then we'll do a dielectric sphere, non-conducting, insulating sphere. But let's do that. So that will be number 2. I'm going to leave this here for the moment. At some point, we won't. Okay. So instead of doing this detail, E dA cosine of 0 for spheres, I'll just go straight to here. It's going to be E times the surface area. E times 4 pi r squared, then the right hand side. Okay? Can I? So I'm going to do number 2. Is a solid. Solid means not hollow with a hole cut out inside, but it's just stuff all the way inside. A solid conducting sphere of radius A and total charge Q. So the total charge is capital Q. I don't know, 5 coulombs, 5 millicoulombs, 10 micro, whatever. So total charge Q. So 2 questions. Calculate the electric field inside and outside the sphere. So, inside and outside the sphere. So let's do the inside first. So here is the conducting sphere. The radius is A. It's a solid. This is not a ring. It's a sphere, right? And it's a sphere, right, all over the place. I'll just make myself some room over here. Suppose I want to know the electric field right there at a distance r from the center. So this would be r less than a, correct? For any r less than a, that's inside the sphere. So what's the electric field over here?
Zero?
Zero. How do you know it's zero?
Because it's on the inside of a electrostatic conductor.
Exactly. We're inside the conducting sphere that's in electrostatic equilibrium. Right? So the answer is zero. Now, suppose you forgot about that. But you remember that the charge would go where? Where would this charge Q be? On this solid conducting sphere. On the surface, right? So the charge would be here. On the surface of the given conductor, right? Now, I wanted to know the electric field there. So I want to use Gauss's law. And in Gauss's law, this electric field is the electric field at the Gaussian surface. So now I have to imagine a Gaussian surface. And I was given a sphere in the problem, so what closed surface do I imagine when I'm given spheres? A sphere, right? So my Gaussian surface is going to be this, and I'm going to use like a dashed. So this thing in blue is the Gaussian surface that I am imagining. Would it be okay with you that instead of writing Gaussian surface, I write GS? For the Gaussian surface? That's shortcut. Right? Suppose I forgot that the electric field inside this conductor is zero. And I said, well, but I remember that the charge goes to the surface. So, well, gee, what should the electric field be inside? So then I use Gauss's law, I do this. So for spheres, we already know the area vector and the electric field is just E times the area. So this would just turn into E times. Now, what is the area? Notice that the A, right, is the area of the Gaussian surface. What is the area of the Gaussian surface that I'm imagining? Is it 4 pi A squared or 4 pi R squared?
4 pi r squared.
4 pi R squared. And just so I don't forget, I always write down epsilon naught first. Now, this stands for the total charge inside my Gaussian surface. Now look at my Gaussian surface in blue. What's the total charge inside of that? What's the total charge inside this Gaussian surface that I'm imagining?
Zero.
Zero. Because all of it is outside on the surface of the given conductor. So, that gives me this result, right? If I solve for E, I'm going to get that the electric field inside is zero. Yes? Okay, now we're going to do the problem outside. So we want to find out the electric field outside the sphere. That's when R is going to be bigger than the radius. So this is the metal. We know that the charge is going to go here, right, on the surface, on radius A. And I want to know the electric field generated over here. Somewhere outside, at a distance r that's greater than the radius of this sphere. So what do? I was given a sphere, so I begin to imagine things. What do I imagine? Another sphere, called the Gaussian surface. Passing through what point? Passing through that point where I was asked to calculate the electric field. So then I imagine a Gaussian surface passing through that point, right? So this thing in blue is the Gaussian surface. It's not there. Remember, it's not there. Just that I'm imagining things. But that's okay. So then I write down Gauss's law. So, if you imagine the correct surface, this just becomes E times an area. So this is E, the electric field that I'm looking at, that I'm trying to find out, right? So at this point, there's an electric field pointing away from the charge because the charge is positive. Then I have to multiply by which area? Do I multiply by the area of the sphere or the area of the Gaussian surface?
Area of the Gaussian surface.
Gaussian surface, whose radius is r. And what is the total charge inside my Gaussian surface in blue?
Q.
Capital Q, the one in red. And the next line is the answer. I just solve for E. And what do I get? 1 over 4 pi epsilon naught Q over R squared, which is KQ over R squared. Kind of nice. As soon as you step outside that sphere, the electric field is the same as if all the charge on the surface of that sphere were at the center, as if it were a point charge. So if I did a graph of the electric field as a function of distance, I have to erase this now. So if I graphed this is R, this is E, this is R equals A, this is 0. So any R less than A, that's inside, right? And any value of R greater than A, than the radius of this given metal, this is outside. Oh, by the way, I just said the word metal, right? Sometimes in homework problems, test problems, they'll say, a metallic sphere. You're supposed to know that a metal is a conductor. It might say a conducting sphere, or it might say a metallic sphere. They mean the same thing. So, what is the electric field expression inside the sphere? It's 0, right? So it's just like this. 0. Stay 0. Now, as soon as you step outside the sphere, the electric field is given by this expression, right? KQ over R squared. And 1 over R squared is like this. So, this one goes as 1 over R squared. So, at the surface, I cannot tell you what the electric field is. That's what the charge is. I can tell you what the electric field is just inside the sphere or just outside, but not on the surface. The electric field is discontinuous at the surface. And it drops as 1 over R squared. Notice that as soon as you step outside the given surface of the metallic conductor, the electric field is the same as if all that red charge were a point charge at the center. It's exactly the same expression. Yes? All right. So, should we do a more interesting problem? Let's make it all that vapor. Let's make it
Like bothers.
a hollow conducting sphere. Can I erase this now?
Yes.
Okay. So let's call this number 3. I think that was supposed to be, I think this was supposed to be number 2 because we did the point charge first, right?
Yes.
So then I'll call this number 3. So a hollow conducting or metallic sphere, all right, with total charge Q, okay, inner surface of radius A, outer surface of radius B, and finally a point charge plus Q at the center. Cool, isn't it? So we have this is radius A, radius B, this is the conductor, this is vacuum here, and this is vacuum. Or you can say air if you like. The total charge on this thing is Q on the metal, but in addition to that, I placed a point charge over here. And the total charge of this is Q. Good? So there are 3 regions. There's the region in this vacuum. There's inside the conductor between radii A and B, and outside the whole thing. So 3 regions that I need to find out the electric field. So the question is calculate the electric field everywhere, in all 3 regions. So calculate okay. So first one, R less than A. That's in this vacuum. Okay? Like I want the electric field, for example, here. Where I put the green dot. So I'm going to do it like this. We have a point charge Q at the center, and then that's the conductor, right? Radius A, radius B. Now, where is this charge capital Q gonna be? And notice, this charge capital Q is not the same as a point charge little q. They're, 5 coulombs and 2 coulombs, for example. Or 5 coulombs and minus 3 coulombs, just different charges, right? So where is it gonna be? This thing has 2 surfaces. Where do you think it's gonna be? The answer is we don't know. But we do know that it has to be either on one surface or the other surface or on both. So let's say it's going to be on both. How about we call the charge here on the inner surface of the conductor? I'm going to give it a name for the sake of argument. I'm going to call that charge Q prime, and the charge on the outer surface Q double prime. On the outer surface. And I do know that the sum of those 2 charges must be capital Q. Right? I just don't know how much is going to go here and how much is going to go there. Because it is actually affected by this Q here. And since I have not given you any numbers, I'm trying to do a general problem, and then, then we'll do some numbers so that you can answer questions in 2 seconds. So we know that Q is equal to Q prime plus Q double prime, right? Are we good? Okay, so I want to know the electric field here, right? At some distance r from the point charge in the vacuum, right? So I draw my Gaussian surface. So the thing in blue is my Gaussian surface. Using color pencils is really useful. So that's my GS, Gaussian surface. I tend to draw my Gaussian surfaces like dotted to remind me that the thing is not even there, right? It's just something that I'm imagining. So here's Gauss's law. So for spheres, I already know that I'm going to take just the electric field magnitude multiplied by the area of a sphere, the surface area of a sphere, right? So this will be E. That's the electric field at the Gaussian surface. And this is the area of the Gaussian surface. What is the area of that Gaussian surface? 4 pi r squared. Not 4 pi a squared, not 4 pi b squared. Right? It's the Gaussian surface. Now, what is the total charge enclosed by the Gaussian surface?
Q, just Q.
The little q. That's the only charge inside this Gaussian surface that I'm imagining in blue is this guy. Q prime is outside of it, and Q double prime is outside of it. It's just the little guy. So the electric field is 1 over 4 pi epsilon naught Q over r squared, which is K little q over r squared. It is just due to the charge at the center.
So to be clear, when it's 0 on the inner wall, it's when it's a solid piece? Or is that just coming next when we do A?
Well, no, we're coming
Okay.
to it.
Okay, sorry.
And then that's the question that I'm going to ask next. Are we good with this here? It's amazing that that result only depends on the point charge Q at the center, not on the big charge, capital Q. Should we do, how about B? So R between radius B and between radius A. This would be inside the conductor, right? Where the meat is, right? Where if you were to eat the conductor, that's what you would bite. Right? So, I'm going to draw it. So, we have so this is A, this is B, this is the conductor, right? I'm going to use red for the charges, so I have Q here, plus Q, and then I have Q prime here, and I have Q double prime there. Yes? And what I'm asking is, what is the electric field here? At some distance r away from the center, that's greater than the inner radius of the conductor, but smaller than the outer radius of the conductor. What's the answer?
0?
Exactly. You're inside the conductor. Right? As simple as that.
See.
You're inside of it, the thing is in electrostatic equilibrium, it's 0. This is not inside the conductor, this is in some vacuum. It's gotta be inside the metal. Right? I know that you can think of this as being inside, but that's not it. That's not what's meant by electric field being 0 inside the conductor. It's inside, that's why I said, I think in my notes, inside the body of it. What the meat is, right? If you were to eat it, right? That's, you wouldn't bite over here. You wouldn't be eating anything. You'd stay hungry. You want to eat this. I'm sorry for that. But, so the electric field is 0 in there, right? That's the answer. Now, suppose we draw a Gaussian surface over there. Suppose that we forgot that, that we are inside the conductor and therefore the electric field should be 0. Suppose. And then we said, okay, well, let me apply Gauss's law. So what would you do? You have spheres. What's the Gaussian surface that you would imagine? A sphere, right? Passing through that point. So this is your Gaussian surface. And then you write down Gauss's law. I hope you people are appreciating. Look at this answer. Can you imagine? How many lines did I write? Gauss's law is given. I wrote this and then this and I'm done. Can you imagine doing this problem by choosing the q's and integrating from here to the point for all of this charge? It's a lot of pages of algebra. A lot. It's painful. With Gauss's law, boom, boom, you're done. Realize that we have a charge distribution over here, right? Yeah, this thing is amazing. So we write this. All right, so this is the electric field at the Gaussian surface, which is E. That's what I'm looking for, right? This would be the area of the Gaussian surface. So, on the Gaussian surface, I gave it a radius r, right? So r is less than the outer radius of the conductor, but greater than the inner radius of the conductor. So what should I multiply that electric field by?
4 pi r squared.
4 pi r squared. And on the right-hand side, what should be in the numerator of this expression?
0.
What's the charge inside by Gaussian surface?
Q and Q prime?
Exactly. I have a little q at the center, and I have a q prime. So this is inside my Gaussian surface in blue, and this q prime is inside my Gaussian surface in blue. The q double prime is outside of it. Yes? And at this point, you have an epiphany. You say, oh, no, wait a minute. Inside, the electric field should be 0. So then you say, oh, no, wait, this is 0. So therefore, what must q prime what must q added to q prime be equal to? So how much of the charge q of the conducting hollow sphere is going to go to the inner surface?
Q.
The negative of what's inside at the center. Right? Because if q prime plus little q is 0, then q prime has to be minus little q. It has to be the opposite charge of whatever was placed at the center. So it's like this charge over here, Q prime, the one that's going to go to the inner surface, has to look in there and say, I'm going to make myself to be the negative of U. Why does it do that? It's like these charges know that the electric field here has to be 0. And the only way to make the electric field here equal to 0 is if this charge is the opposite of that, so that when you do the Gaussian surface, you get 0 charge enclosed. So then the electric field inside is 0. It's like the charges know. I mean, it's gotta be cool, isn't it? Now that we know how much charge goes to the inner surface, therefore, how much charge is gonna go to the outer surface?
Q.
Now we can figure out how much is going to go to the outer surface, right? Well, this is what we were given. Now we know that that's going to be the opposite of what was put at the center. So now we can get this. Now, do I memorize those results? No. What is easier for me to remember? That the charge on the inner surface is the opposite of what's at the center. And whatever is left is going to go to the outer surface. Period. That's easier for me to remember. Not a formula like this. I don't want to do that. It's easier for me to think the charge of the inner surface is going to be the opposite of what's at the center, to make the electric field inside the body of the conductor equal to 0. And then whatever charge is left over, whatever charge the sphere had, the conducting sphere had, is going to go to the outer surface. So are you ready for this? For the 2-second answer? Or maybe 1 second? And I mean it. I'm not kidding. Just from understanding the concept. Okay. Inner surface, outer surface. So this is the conductor. Okay? And there's a point charge at the center. Little q. Okay? And there's a total charge q given here. I mean, that's the total charge of the conductor. Now, what we're going to do is, we know that some of the charge is going to go to the inner surface. Which is q prime. And the rest of the charge is going to go to the outer surface. Okay? So, what would you like this charge to be? I'll let you choose. 5 coulombs? Cool, I like it. I was born on September 5th. Same as Freddie Mercury. I like to break free. I actually saw them in concert at the Madison Square Garden when I was taking physics, like you guys. Unforgettable. Of course, the last song they played was "We Are the Champions." Are you ready? Or are you ready? From the moment that I tell you the value of q, little q, in 2 seconds you have to figure out how much this is and how much that is. I'll make it simple. Okay? Are you ready? 5 coulombs. The whole thing is 5 coulombs, right? Okay, simple. Oh, come on.
Q prime is 2 and Q double prime is 3.
How much?
Q prime is 2, and then Q double prime would be 3.
Of course. This has to be the opposite of that, and then 2 plus 3 has to give me the 5. Yes?
Yeah.
Let's do another one for your honor, okay? Okay? So notice how in that case, of the 5 coulombs, 2 went to the inner surface and the remaining 3 went to the outer surface. And 2 went here to cancel that so that the electric field here is 0. It's cool. Okay, are you ready for that? Okay, another simple one. One and 4, right? Simple, huh? Another one?
Negative 3 and 8.
Negative 3, and therefore this has to be 8.
No, because Q1 plus Q2 is Q.
Yes? 8 plus negative 3 gives me the 5. Another one?
Please.
Are you ready? 0 and 5.
I was stopping there.
This is when all of this charge, none of it is going to go to the inner surface. All of it is going to go to the outer surface. Last one.
Five and 10.
I'm getting 0.
Wait.
I said 10 too, though. I said 10.
No, that's too long. No, that's too long.
Nah.
5 and 0.
This is when all the charge in the conductor is going to be drawn into the inner surface with nothing on the outside. So, how will the charges distribute? In between, there's an inner surface and outer surface. It depends on the other charges around, right? This will determine how much charge goes here. And then whatever is left over to make this the total charge of that conductor has to go to the outer surface. With the purpose of making the electric field here 0. So if you're ever in a car and it's raining hard, and I don't know, maybe you went out with someone and you were outdoors and just near the car, and then it started to rain really hard, and you see lightning go inside the car. Go inside the car. Don't touch any metal, but go inside the car. Because if the lightning hits the car, it's going to go on the conducting metal of the car and it's going to go to the ground. And you're inside, you're going to get spared. It's like the charge is going to go, I'm going to protect you going in there. And then go to the. So.
I'm dumb. I would accidentally touch metal. Yeah, I'm not that
No, you
smart.
might grow hair.
There's something there.
There's a nice video on YouTube, but maybe next time I'll show it to you. It's called "Car Gets Struck by Lightning." So this is a BBC program. I don't know if you've seen this. So the British, a guy goes in a car and then they set up he goes to some lab in Germany they create, like lightning, and the guys in the car like, and it's amazing.
That's crazy.
Okay, so tonight we're going to, well, half of you have lab, right? At 6:45, I think. I wanted to do something having to do with oscilloscopes. So instead of you running some simulation and reading something from a screen, you play with it. There are parts to the experiment which involve a microphone, and I found the microphones, all the batteries. So let's do the part without the sound. Because an oscilloscope is an instrument that is used to display voltage signals. And we'll be talking about voltage in the next chapter, 23. And I wanted to just send in various voltage signals to the oscilloscope so that you could measure that. So you learn to use an oscilloscope, at least at the most basic level. And with a microphone, it's kind of nice because then you connect the microphone to the input of the oscilloscope, and the microphone converts your sound signal into an electrical signal, into a voltage signal that then is displayed on the oscilloscope. And we can figure out, for example, if you whistle, if you go like, actually that's not as clean as he. That's actually more monotone. And then, what's the frequency of that sound? So we can use an oscilloscope to figure out the frequency of he. How do you know if that's 800 hertz, 1000 hertz, 50? How do you measure the frequency of a sound wave? So first, I give you a tuning fork that you hit. Bong. It's annoying. But we know what the frequency of that sound is. It's actually written on the tuning fork. And then I want you to measure it on the oscilloscope, and then you can compare, do percent error. But then, as a second sound signal to display on the oscilloscope, I don't know what that's supposed to be. So you measure it, but I don't have anything to measure it against. So you just, whatever it is that you measure, you get the practice from the tuning fork that you know what it's supposed to be. And if you get something very close to it, then you know how to measure it, and then you can measure the frequency of this other sound. Unfortunately, the batteries are out. So that part of the experiment we'll do, let's say, next week, something like that. But the other parts where we have a function generator that generates a voltage signal, and we also have like a DC battery, and we can at least display those signals, voltage signals on the oscilloscope, and just play with that. Okay, so unfortunately, I found the microphones, but I couldn't find a battery that works. If I find one that works, then at least maybe some of you can make a measurement on it, but I have to find, if not, I have to buy batteries somewhere. So that's the plan.
Are we planning on having a quiz in the near future?
Yes. When would you like one? Chapter 21. I can give you one this Wednesday, or I can give you one next Monday.
Can we do it next Monday?
Yeah.
Can we get adjusted to in-person class first?
Okay. So next Monday I'll give you a quiz. My quizzes are, you have 20 minutes, one question.
10 minutes?
Huh?
10 minutes?
Sorry, 20 minutes.
Oh, I heard
20
two.
minutes. Maybe I said 10. I give you 20 minutes, and it's one question, and then you work on it, and
then submit it.
And then that's
then
it.
submit it.
Yeah.
I haven't decided yet if I want to collect it and grade it, or if I want you to upload it. But I don't know. Then you have to bring like a laptop or something. I mean, how do you guys? You can use your phone to upload it too, right? So if you want to do that, then that's actually easier for me. And then and instead of grabbing paper and then I don't want to give something back to you and give you something, right, that you're not supposed to catch. Right? So, it'll be safer for all of us, I guess. So I'm gonna have to. So next Monday, remind me on chapter 21, right? So I'll probably give you a couple of, point charges and find the electric field somewhere. So no big deals. But you have to know how to add vectors. If you're a little rusty on finding the components of a vector, and You have to know that.
Sounds good.
Sounds like a plan?
Sounds good.
Okay, so I'll see half of you later tonight, I think. All right, but the rest.